So today we'll continue with our discussion of the p-n junction electrostatics. And we stop here. Can everyone see the class notebook? Online. Okay. So we have p and n junction. Just a brief recap. We have a p and n junction caused due to the PA type semiconductor and n type semiconductor coming in close proximity, right? Coming in contact. And so there is a diffusion of charge carriers that takes place across the junction. The majority charge carriers, electrons on the n side and holes on the p side will cross over the junction. That activity would continue until the entire charge is evenly distributed throughout the entire PN junction, throughout the entire PN type device, okay? But that's not what happens. The diffusion current is actually stopped. So let's take a closer look at what happens near the junction and around the junction. So here's a close-up view of the junction itself, right? As the electrons move from the n side towards the p side, they are going to leave behind ionized atoms, right? The electrons are free to move, so they move over to the p side, they diffuse into the p side material, they leave behind ionized atoms. Now, because it lost a negative charge, has a positive charge left behind. But that charge, that positive charge, which is indicated here, these are immobile, right? They cannot move. They are atoms that were diffused into our semiconductor material. They are fixed in spot, or fixed in place. Same thing happens on the p side. We have holes that diffuse through the junction and move over to the n side material, leaving behind ionized atoms with negative charge. Okay. And so what happens is this creates a region of charges known as the space charge region, SCR. Space charge region. That is right here. So you have ionized atoms on both sides, the p side and the n side. Okay. And these charges cannot move. They are fixed in place inside the silicon lattice. Okay, because these are atoms that displaced other silicon atoms and took their spot. And this space charge, this space charge region, because it has positive ionized atoms on the n side and negatively ionized atoms on the p side, give rise to an electric field. There is a gradient, right? You have positive on one side, negative on the other side. Gives rise to an electric field. That electric field causes the drift of the charge carriers, causes a drift current, and the drift current is in direct opposition to the diffusion current that initially created the space charge region. You all with me so far? Okay. So let's recap. We have a p-type material, n-type material coming into contact. Because of the gradient of charge carriers from the p and n side and the n and p side, the electrons from the n side n-type material and the holes on the p-type material diffuse through the junction. This phenomena would continue until stopped, or it would continue until everything is even, until the charge is evenly distributed. So that diffusion current gives rise to a space charge region near the junction. That space charge region consists of ionized donor atoms with positive charges on the n side ionized acceptor atoms on the p side. That gives rise to an electric field. That electric field causes the charge carriers to drift in response. And because they drift, it causes a drift current. The direction of this drift current is in direct opposition to the original diffusion current. And then that puts a stop to the diffusion. Okay, stops the original diffusion. And this is basically the key factor in how a diode or semiconductor works in just one direction versus the other. Okay. If you graph this, if you plot the charge density on the N side, so this is the N-type material, this is the P-type material. If you plot the density of charges, it would extend deep into both the N-type and P-type. But again, remember, it's charge neutral, right? The number of charges would be neutral. The difference is because of the number of atoms that are used for doping. So in the example that we are using, the doping was 10 raised to 16 atoms and 10 raised to 17 atoms. Okay. So we have charges that are present in the N and P-type material diffused into the junction, diffused into the semiconductor material. That causes an electric field. The electric field also again extends to the depth of the implant. And that electric field gives rise to a potential. And this potential is labeled as phi j, Greek letter phi, and j for the junction. This is also referred to as the built-in junction potential. And it depends on the material that is being used to create the PNN type semiconductors. So if we create a PN junction diode using silicon, this built-in potential is approximately 0.6 volts to 0.7 volts for silicon. Actually, it should be the other way around. For silicon. For germanium, it is around 0.2 volts to 0.3 volts. This is the amount of voltage that is required to overcome the built-in electric field that is automatically created. All right, let's take a pause, think over all of that, and let me know if you have questions. Yes. And I was going to say that, no, not the talk, but I would say assign reading in the textbook. So students, if you wish to explore the topic a bit further, go through the assigned reading in both the books. There is one for credit, for extra credit in Jaeger, and the other one is in Franco. So Jaeger goes a little bit more in depth. Franco, yeah, Franco also has that. So that was going to be part of the assigned reading. Chapter 2, I think, when I assigned it, well, it's too late now because students already started it. But I wanted to break it down. But before I could break the assignment down into different sections, the reading assignment, I mean, students had already begun, so I couldn't modify it. So it's like one big chapter. But again, my assumption is everybody is, and adult college students, so they would know how and when to keep up with the class material. And then Jesse, you had a question, and then there was a hand. Okay, you had it. Okay. Yes, electrons. It's just summed up that way because we are taking the X direction. Oh, you're talking about you're talking about this positive charge right here. It's because it's a donor atom. So it's left behind with positive charges on the N side. Yeah, so hold on, let me summarize. The question being asked is, if in the N-type material majority carriers are electrons, why are we showing a positive for N side and negative for P side? It's because the space charge region creates positive ionized atoms on the N side and negative on the P side. And so it's summarizing the space charge region because that's where the electric field comes from. Yes. Yeah. The whole drift and electron drift. Yeah. The whole drift and electron drift is basically due to the, yeah, exactly, the space charge region. Yes. Yeah. Diffusion is because of concentration gradient. Drift is because of electric field. She had a question, and then you next. Oh, depth of implant. Depth of implant. So implantation is a process of, well, introducing our impurity atoms into our semiconductor. So there are two ways to do that. We force it in, which is, to use a violent imagery, it's like shooting bullets at a wall or at a target. You're just forcing it. So it's an ion beam, and you just shoot ions at your surface, the wafer surface, and it implants atoms into the wafer surface. And that's called ion implantation. And the other process is diffusion. In diffusion, the dopant is in liquid form. You spread it on the surface of your silicon wafer, and you stick it in a furnace at 1000 or 1100 degrees C. And then at that high temperature, the dopant will diffuse into the surface of the wafer. So those are the two processes by which we create, hence the depth of implant. It's how deep into the surface the implant impurity would go. And then you had a question. So what happens to the drift current? I mean, what happens to the diffusion current that began the process? And then how is the drift current? Am I understanding your question correctly? Yes, yeah. So right here, probably I glossed over this. And so it begins with a diffusion current because of the concentration gradient. The diffusion current is because of the diffusion of charge carriers. That causes charge density variations. That creates a space charge region because there's positive charges on one side, negative charges on the other side, gives rise to an electric field. The electric field causes the other charge carriers to drift in response. And this is all built in, meaning as the moment we have P and N type material together, takes place instantaneously. I mean, as soon as in the fabrication facility, we implant it, it's done. And so that drift current, the drift of the charge carriers give rise to the drift current. That drift current is direct opposition to the original diffusion current. It opposes the original diffusion and it comes to a stop. I think that's the answer to your question, right? Yeah, it comes to a stop then. Yes. Yeah. Yes. Yes. So the question being asked is phi j, which is basically a result, is the voltage or the built-in potential that is a result of that electric field, is, what was the second part of your question? So the question being asked is the drift current opposing the diffusion? Okay, gotcha. So is the built-in potential in the electric field opposing the flow of current in the forward direction? The answer is yes. At this point, this is simply, let's say this is a wafer, we stuck it in a furnace, we introduce impurity dopants in there. That's where we are right now. So in the fabrication facility, when this is being manufactured, we have our silicon wafer, we introduced, let's say it's a P-type silicon wafer, we introduced N-type dopant impurities in there. As soon as the diffusion process is finished or the implantation process is finished, our impurity dopants are in there. We now have a P-N junction right there in the silicon wafer. And this is what happens. This is without doing anything else, meaning this is at thermal equilibrium or just equilibrium. That's where we are right now. Yes. Breakdown voltage would be different. And we'll get to that in a few slides. Okay. But does everything make sense? Okay. Now, remember I said we are learning about integrated circuit, circuit design basically with diodes and BJTs and FETs. So 307, 308, you'll be doing that, a lot of circuit analysis. So chapters 1, 2 are pretty much, just devoted to the solid state physics of the devices. But then from this point on, after we get done with this topic, probably on Friday or Monday, then we'll move into circuit analysis. Okay, so the space charge region is depleted of all charge carriers. Hence, it is known as the depletion region. And it creates a depletion region of a certain size. And so depletion region width is given by WD0. So the depletion region width WD0 would be how far it extends into the N and the P type material. So XN and XP. Excuse me, sorry. Oh. And that is given by square root of 2 epsilon S over Q. And then, of course, it's dependent on the actual doping amounts. So ND and NA, which is basically controlled at the factory. Okay, so depending on what kind of diode you want to create, you would back calculate and determine what kind of doping would be required. So NA and ND, let's break it down. And phi J, of course, is the junction potential. NA and ND are the number of atoms per centimeter cube. And I've stated this earlier and I'll state it again. When I was a student, and even now, when I want to perform any calculations, I convert everything to a single metric, meaning if it's centimeters, I convert it to meters. If it's kilometers, I convert it to meters. If it's Microns, I would convert it to meters. So 10 raised to minus 2, 10 raised to minus 6, and then I would perform my calculations. When you do the homework, pay attention to the units, because many of the solutions would ask you to enter the answers as centimeters. So then the constants that we use would have different multipliers or different exponents. So epsilon s is the permittivity of silicon and it's given by epsilon r times epsilon 0. I should have epsilon r times epsilon 0. Epsilon 0 is a constant. Epsilon r depends on the material. Okay, so again, everything would be given to you, or if it's not given to you, you can always look it up. Epsilon 0, and the reason I was pointing out the earlier thing is epsilon 0, which is absolute permittivity, is 8.85 into 10 raised to minus 12 farads per meter. If you do centimeters, it would be 10 raised to minus 14 farads per centimeter. So just keep that in mind. For silicon, I believe epsilon r is 11.7. It is a ratio of the permittivity of the material with respect to epsilon 0, so it doesn't have any units. Okay, epsilon r doesn't have any units. And then phi j, of course, would be volts, but the final answer here, I'm just stating in meters, but if you're performing the calculation, the online system might ask you how much it is in centimeters. Okay, so again, pointing that out, because every time students do it, this is something that I've encountered in the past. Got the answers wrong, got it incorrect. This is the reason why. Okay, and again, phi j, of course, also depends on the concentration in A and D. And of course, it depends on the intrinsic carriers, hence Ni square. That's why it's different for every different material. And Vt is the thermal voltage. Einstein's relationship is given by KT over Q. And units for this should be volts. Okay, so I think the next homework, if I recall correctly, there are questions about WD0, and then Friday's quiz be some material from today, some from Monday, and some from Friday. All right. All right, so if you want to calculate the built-in potential, calculate the built-in potential and the depletion region width for a silicon diode, we are given Na and Nd. This is where we would apply the equations. So this is an example. I believe it's already solved in the book, but I'm going to go over, I won't go through the entire thing, but we'll just go through the equations for all three of them. Ni, the intrinsic for silicon, it may be stated, it may not be stated. If it's stated, you simply take that value. If it's not, you assume, because this is pretty much well known. Okay, for silicon, and if no other information is given, you can always make assumptions. So in this case, just from the face of it, we don't have the temperature, we don't have Ni. So we simply assume it's room temperature 300 Kelvin, and we'd assume Ni. Okay. So either it's given or simply assume. Assume is also not even the right word, because again, these are all based on device physics, laws of nature. So there's not much variation in those values. So Ni can be taken as 10 raised to 10 atoms per centimeter cube, or not atoms, sorry, charge carriers per centimeter cube. Thermal voltage VT, our book sticks with 25.8 millivolts, 0.0258. So I also tend to stick with whichever book we are using. Okay. Some books use 25.9, they round up. Some books just use 25 millivolts, just to make things easier. But since the book uses 25.8, we can run with 25.8. And then it's simply plug and solve. We have equations for Xn, Xp, WD0, and Emax. Emax is, of course, the electric field that is generated automatically. So let's see, Xn. I thought I had equations for Xn and Xp. Okay, all right, I'll write it out here anyway. Xn is WD0 divided by 1 plus Nd over Na, and Xp is WD0. It's not quite right. Divided by 1 plus Na over Nd. Right, Xn is how deep into the n-type material it goes. And so it's the number of donor atoms divided by the acceptor atoms. And then for Xp, it's the exact opposite. Yes. The equation, I didn't invent them. Straight from the book. I mean, straight from any book, basically. So there are some derivations involved. But again, just, you know, if we go and try to do all the derivations, we would never require like maybe the whole entire academic year to get everything done. So again, I would say that is why the assigned reading comes into the picture. And then Emax, the electric field that is generated, is 2 times phi j for WD0. Okay. So assign it as student practice. Also, to answer your question a little bit further, I believe I mentioned this last class too. There is a higher level course, EE 534, 524, solid state electronics. And therein we have time to go in and do all the derivations and look at every, everything that's going on at the atomic level. All right, so what this does is it results in a very non-linear characteristic. Okay, so this is where we can look at, and I'm going to exaggerate this characteristic. Because of the built-in potential, there is no current flow in the diode. And I'm exaggerating the slope, okay? I'm exaggerating the slope. And we'll again look at this at zero bias, in reverse bias, and in forward bias in the next few slides. But we just want to point out the IV characteristics. So the voltage, this is the current. So we are showing a plot of the current as a function of the voltage. In linear circuits so far, you increase the voltage, current increases. You decrease the voltage, current decreases, and vice versa. Diodes, BJTs are nonlinear devices, meaning the current and the voltage not have a linear relationship. You increase the voltage in a diode, current still remains zero, as you can see here. And then the voltage rises to a level that is enough or sufficient to overcome the built-in junction potential, is indicated right here in this graph. And in this exaggerated graph would be here. And this is the value of the voltage that is required to overcome that electric field. This is known as the turn-on voltage. It's straight down. This one, right, is just an exaggeration. Yeah, it's just an exaggeration of the slope. Exaggerated. This is the turn-on voltage. It is also known as the knee voltage. Simply the diode voltage. It's the voltage that is required to turn it on in the forward bias. This is shown right here. In the reverse bias, you would expect that the diode is not going to conduct because we have the depletion region. And the depletion region actually widens because of the reverse bias that is being applied. Near the origin, if we zoom in, we can observe that the characteristic actually goes or passes through the origin at 0, 0. So this right here is this point that is pointed out. Yeah, let me just write, this is figure 3.9. When we zoom in, you can see something known as IS. And IS is the reverse saturation current. That reverse saturation current is the result of minority charge carriers crossing over the junction. Typical values range from the order of like nanoamps, picoamps, and femtoamps. So it's very, very small. Okay. So IS is very, very small. But again, IS is a result of the diode fabrication. Okay. Diode fabrication and the material properties. Diode fabrication and the material properties. Especially if you have heavily doped PN junction diodes. If you have heavily doped diodes, you have more charge carriers. And that causes a different kind of effect in reverse bias. And we'll talk about that in just a bit. Okay, any questions? Yes.
At some point you have like a built-in potential, so you apply voltage, and like as soon as it crosses over that threshold, you start getting right. That's what the
Charge carriers, and we'll look at each case individually in next few slides. This was just to introduce the diode, as in, just to show it's a diode is a nonlinear device, and how would the current work as a function of the voltage. And so that's zero bias, reverse bias, and forward bias is coming up. So we can describe the function of the diode or the diode current as a function of the voltage ID versus VD. This equation is known as the diode equation. It is also known as the Shockley equation. Okay, Shockley equation. So basically, ID is given by IS times e raised to VD NKT minus 1. ID and VD are the diode voltage and diode current. IS is the saturation current. K is the Spence constant, and T is the temperature in Kelvin. N is a factor that describes the non-ideality of the diode. It's typically 1 or 2, and it's given by the manufacturer. Non-ideality factor of the diode. Typically, it's always 1. Most of the equations, we always take it as 1, unless the diode manufacturer specifies it's 2. Diode equation or the Shockley equation. So then let's, oh, yes. Not necessarily. Better is relative, depends on our application. It just depends on the application. For the most part, the regular diodes we use, it's always 1. All right, zero bias. Zero bias means we have, remember I said, in the fabrication process, in the manufacturing process, we took our wafer, we implanted some dopant impurity in there, and we created a PN junction diode. Okay, we created a PN junction. I said, at that point, once temperature cools down, an implantation process or the diffusion process is complete, we have a PN junction. If we run some measurements on it without applying any sort of external electric field, any sort of external stimulus, that is what zero bias means. The semiconductor material is at equilibrium. The intrinsic carrier generation due to charge carrier, due to temperature effects is the same as the recombination rate. Everything is paused or everything is stopped. Okay, that's equilibrium. The net flow of charge is 0 and current is also 0. So the first thing is no external stimulus. And then if you're using diffusion, ion implantation is not a high temperature process. But if you're using diffusion, actually, after ion implantation, we do a high temperature anneal. So it does go up to high temperatures. When it goes up to high temperatures, what will happen? Oxide layer forms, yes. But what happens at the atomic level, the electrons subatomic level? Exactly. So more covalent bonds are broken. So we are sticking our wafers in a furnace at 1000 degrees C, right? T is large. T is now 1273 Kelvin. And so you have more bonds being broken, more intrinsic carriers generated. Then as it cools down, those electrons are now going to recombine with the empty holes. And so that's carrier generation and then recombination. So once it reaches room temperature, the rate of carrier generation is equal to the rate of recombination. At some point, it's going to equal out and stop. And so at that point, our device is at equilibrium. There are no more intrinsic carriers being generated. Okay. So at equilibrium, carrier generation rate is equal to recombination rate. Recombination rate. And that's at thermal equilibrium. And then hence net flow of charge is equal to 0. We are not applying any external stimulus. It's the built-in potential. This is right when the device is created. fabricated or manufactured. Okay. And so current is equal to 0. So the depletion region width exists right now just due to the amount of doping and the type of material that we are using. And in the clean room class this quarter, we are, where are we right now? We created an oxide layer on top. And this week, or no, next week, we're going to diffuse our diffuse our impurity atoms into our silicon wafer. That's supposed to be done next week. We'll see how it goes. All right, reverse bias. What happens in reverse bias? If we apply negative voltage to the negative voltage to the p-type material, meaning the anode. Let's look at what happens at the subatomic level. Right. This is a depletion region that exists because of the doping. This is the p-type material. This is the n-type material. The excess of positive charges here, excess of electrons here. And then we are applying negative p-type and positive to the n-type. Just one explanation. Here I'm using the words apply negative to the p-type and apply positive to the n-type. The actual explanation, not actual explanation, but the larger explanation would be we are simply taking the p-type material and elevating it at a higher potential level than the n-type material. I mean, the other way around. N-type material is at a higher potential than the p-type material. So you could potentially apply 3 volts on the p side and 10 volts on the n side, both positive voltages, but it will still be reverse bias because the n side is higher in electric potential than the p type. Okay, that's what reverse bias means. So what happens? Electrons are negatively charged, holes are positively charged. What happens when you apply an external voltage with opposite polarity? Opposite charges attract. So they're pulled away from the junction. And because they're pulling away from the junction, the depletion region widens. Okay. Depletion region. And I would say the space charge region increases. Now you have more ionized atoms created in the n side and the p side. So the space charge region is extending, it's expanding. Depletion region widens. Now, theoretically, we would say it would continue indefinitely, but that's not what happens. At a certain point, the electric field that is being applied would exceed a certain amount that it can withstand, and the junction would actually break down because there are so many ionized charge carriers that are being generated that now they will actually cross over in the reverse direction. And a large amount of charge carriers will flow through. And in the reverse bias, there are 2 effects that we'll look at later on, is Zener and avalanche breakdown. And so we'll look at that in just a little bit. But this is what happens right now, right? Only minority carriers are crossing over the junction. And that causes a reverse saturation current, which is known as IS. Minority carriers mean holes on the N side and electrons on the P side, right? And so they would actually be repelled by the external voltage. And because they are being repelled, they cross over in the opposite direction of the majority charge carriers. And the current that results is IS. We have a few more minutes. That's the reverse saturation current. Okay, let's take a look at forward bias, then I'll open up for questions. So in forward bias, this exact opposite happens. N and P, H plus, H plus, H plus, negative electrons. And we are now applying a positive and positive to the P type, negative to the N type. And so now the majority carriers are being repelled away. And so they are moving into the junction. And because they are moving into the junction, these majority carriers will now recombine with holes and electrons that are present. The depletion region would shrink. And because it's shrinking, at some point, go to zero, and the charge carriers are able to cross over the junction, which results in a high current flowing through the junction in forward bias. Okay, so there's electrons here, and there's a space charge region right here, or the depletion region, right? So you have ionized atoms, positive atoms right here. And it's ionized negative atoms right here, right? And so if you're pushing the electrons away, meaning they're moving in this direction now, they're going to combine with some of the ionized atoms. The electrons are majority carriers, so there's a large number of those electrons on the N side. And the ionized atoms, even though they are large in number, they are very small compared to the number of electrons that are now being pushed into the junction. So some of them will recombine. The space charge region will start diminishing or reducing in size. And then the rest of them have nowhere else to go except go forward and cross over into the junction. And holes go in the opposite direction. So we would have to go back to the space charge region where the larger image a few slides ago, where we had the ionized donor atoms, the positively ionized donor atoms in the N side, and the negatively ionized acceptor atoms on the P side. So if electrons are being pushed towards the junction, then some of them will recombine in the space charge region, takes out a bunch of ionized atoms. Space charge region is now decreasing from both sides. And at some point, the large number of electrons that are coming through are going to completely shrink the junction. All right, so let's take a pause, open up for questions. Yes. So the minority carriers are due to the intrinsically generated carriers. And so they are fixed in number, unless there's some external doping also done, which happens in like reverse breakdown diodes. So that reverse saturation current is solely due to minority charge carriers in both P and N type material, and they are pushed through the junction because of the reverse bias. So here, where the majority carriers are pulled away, let me make a note here. So the question being asked is about reverse bias. Majority carriers are pulled away from the junction. And minority carriers are pushed towards the junction. It's the same effect that occurs in forward bias and reverse bias. except the majority charge carriers and the minority charge carriers switch places because of the polarity of the applied voltage. And so there's heavy current flow in the forward bias and very small current flow in the reverse bias. Does that make sense? Does that answer your question, or did you have a? Okay. Minority carriers are pushed towards the junction. To get better at writing. The opposite occurs here. Majority carriers are pushed away or pushed towards the junction. And minority carriers are pulled away. And thus, we have small current flow in the reverse bias and large current flow in the forward bias. Yes. Sure. Yes. Oh, we are actually out of time. I'm here for questions, but we'll end class here today. Please keep up with the assigned reading in the textbook. And again, as I said, there's some derivations in the textbook. And if you have questions, just reach out. Okay. Honestly speaking, I would have to say there